that was just a review, so you can't complain about that. All right, yeah, that's good enough. So the second law, let's see. So what do we know about the change in entropy if the temperature of a system is not changing, but heat is entering or leaving? How can we express the entropy? Does anybody remember? So we can say that change in entropy is equal to the heat over the temperature. Of course, if the temperature is changing, then we can just relate Q to the specific heat and then do some kind of integration here. So let's take this. Let's look at the hot reservoir, first of all. So for the hot reservoir, its change in entropy is just going to be the heat that leaves. I'll put an explicit minus sign here because this heat is leaving the reservoir, and the hot reservoir is at temperature T. For the cold reservoir, we just have the same expression, but obviously now heat is going in, and T is the T cold of the reservoir. So what does the second law of thermodynamics tell us? Well, if we apply it, it tells us that basically the total entropy can either stay the same or increase, right? So if we add these two up, it has to be greater than or equal to 0. So if we take these two expressions right here, we can turn this into the following relation between the two expressions. So we can say that QC is TC, QC over TC is greater than or equal to QH over TH by the second law of thermo. And so if we rearrange this a little bit, we can say that QC over QH is greater than or equal to TC over TH. So just relating the two heats that are going in or out of the reservoirs to the temperatures of the reservoirs. And so now, this expression that we had on the previous page right here in terms of the heats, we can write it as an inequality. And so we can say that the efficiency is not anymore just equal to something, but it has to be less than or equal to 1 minus Tc over Th. So the efficiency is completely determined by the relative ratio of the temperatures of the reservoirs. So how could we possibly get the most efficient heat engine possible? What would we want to do here? We want to either send T cold to 0 or T hot to infinity, or you could do both at the same time, right? But as long as you can maximize how far apart these two are, you're going to get the most efficient process possible. So let's calculate this just for like some typical values. So let's say we've got TC is 300 Kelvin, something around room temperature, and TH is 600 Kelvin, which is getting pretty hot. What is the efficiency? Well, the efficiency has to be less than or equal to 1 minus 300 over 600, and the kelvins cancel out. This just gives an efficiency of a half if you have it operating between those two. And note that this is an inequality. So it doesn't say that the efficiency is equal to a half. It just says that the best you could possibly do is a half. So if there is somehow extra entropy created in this heat engine, then typically the efficiency will be less than 0.5. This is just the best you could possibly do. So does anybody have any ideas about how you would generate extra entropy? So I mean, you can definitely visualize like how you would get this to be equal, like somehow you're just able to transfer the heat from one to the other without like any intermediary. But in general, we're going to have some kind of like gas or engine that actually has its own temperature, right? Oh, I see you chat. Friction, yeah, friction would be a way too, yeah. So I mean, in general, in like real engines, which we won't actually talk about in any detail, there's going to be some kind of piston that's moving, and it doesn't perfectly just like glide along the wall in a frictionless way. So it creates some heat in that movement, and it creates some extra entropy as heat. And therefore, this efficiency is not ever going to reach its maximal ideal value of a half. Okay, so now we're going to talk about the Carnot engine, or the Carnot cycle, or how to construct the perfect heat engine. Carnot cycle. All right, so we're gonna now talk about how you would actually construct a real engine, real in quotations, because a Carnot cycle is slightly idealized, but it's something that you can fairly well approximate. It's just not super useful in practice, and we will show why. So basically, in a real engine, you need something that absorbs the heat, right? So there needs to be some kind of material in this engine. So I mean, you've got an engine compartment, heat goes in, and then something in here has to actually transfer the heat from there to there. So that thing, at least in a Carnot cycle, is going to be a gas. So the first step of the Carnot cycle is going to be that heat leaves the hot reservoir, which is sitting right here. So this is TC. So we'll just say it leaves TC, or sorry, not TC, TH. Hot reservoir. So we'll just use TH to denote the hot reservoir. And it decreases the entropy of the hot reservoir by QH over TH, right? We just wrote that before. So now the heat leaves there, it decreases this entropy, gets absorbed by the gas. Well, if we don't want any extra entropy to be created in the process of going from here to here, we need to have the temperature of the gas be basically the same temperature as the hot reservoir, right? Because otherwise, what happens? Well, the heat, it goes in, and if, let's say, like T gas is less than TH, well then the change in entropy of the gas as it absorbs this heat, so it gets QH. But if that's at TG, then it definitely has to be greater than the entropy that leaves the hot reservoir, right? So if this is smaller than TH, then it has to gain entropy. So we do this weird thing here where we assume that TG is just small enough, it's close enough to TH so that heat will actually flow from the hot reservoir to the gas, so it has to be lower, but it's not low enough to actually create any entropy. So it doesn't really make any sense, but it's an approximation. So yeah, well, yeah, we're basically trying to construct the most efficient engine that we possibly could. And so the only way you can do that is not by creating any entropy. But yeah, if you did create extra entropy, you would have to dump it as heat, right? So this is just an idealization of a process called the Carnot cycle. It's not something that you can exactly recreate in real life, but you can do something that is very close to this. It's just not super useful. Okay? So we're assuming this right here. Just that it's a little bit less than TH, so that the change in entropy here we can just completely neglect. It's the same as that. I guess I shouldn't put an X through there. So that it is equal. Okay, so that's how we get it, just by assuming this right here. And as the gas absorbs the heat, we're going to say that the gas stays at its initial temperature, that is just slightly less than TH. And the way it does that is because we allow it to isothermally expand. Okay, so heat flows from TH to TG, so the temperature of the gas, and as it goes in, the gas expands isothermally, so it keeps the same temperature that's just a little bit less than the hot reservoir. Okay, so that's one step. Another step that's important is going to be when the gas transfers heat to the cold reservoir. So the cold reservoir is over here, TC. That's where our waste heat goes, which we call QC. And you get your work. So again, we don't want extra entropy to be created in the process of heat being dumped from the gas to the cold reservoir. So what do we need to assume? Well, we need to assume that Tc, cold reservoir temperature, is just a little bit less than T gas. So that heat will actually flow from here to here, because you need to have a temperature differential for it to actually flow. But we're going to approximate this as being small enough that no significant entropy gets created. And again, as this happens, as the heat is dumped from the gas to the cold reservoir, it has to now isothermally contract, right? So again, the gas stays at Tg. And the way you get that is isothermal contract. Okay, are there any questions about those two steps? No? Okay. So we've got, we know how the energy goes, or the heat goes from the hot reservoir to the gas, and how it goes from the gas to the cold reservoir. But now we need to figure out how to go in between those two different temperatures, right? Because the gas isn't just at one temperature the whole time. I mean, it has to be roughly at T hot, and then it has to be roughly at Tc. But you obviously don't want TH and Tc to have to be roughly the same thing. So what do we need to do? So the question is this: how does T gas change from roughly T hot to roughly T cold? Well, this is a closed system, and thus heat cannot flow in or out of the gas. It's completely closed. So therefore, we're definitely going to need some kind of adiabatic compression and expansion. In order for this cycle to work. TH and TC. Okay, so what does this look like? Well, if we draw a PV diagram, our full Carnot cycle now is the following. So you start at T hot, and you've got, I'll do my best to draw like an isotherm right here. That represents T hot, and an isotherm down here. Well, it's actually more like over here. Something like that. It shouldn't be curving up. Oh God. What? No. Why? Okay, just take for the moment that these are isotherms. So that's T hot, that's T cold. So we slide on down here on the isotherm as the gas expands isothermally. So it starts up here in contact with the hot reservoir, takes on heat, expands isothermally, goes down to here. Well, now we've got to get it to T cold. So we need an adiabat, and this is a horrible, horrible picture, but just grant it that this is going to be an adiabat. My scaling here is very nonlinear. Should actually be there. So you've got an adiabat that takes you down from this temperature to this temperature, at which point it interacts with the cold reservoir. And then it dumps heat into the cold reservoir and isothermally contracts. And then in order to get back to its starting point, it adiabatically compresses and goes up to the higher temperature, at which point it interacts with the hot reservoir again, goes down, blah, 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 goes round and round and round. Okay, so you might ask, well, if these energy, and we're not necessarily showing here that like a straight up derivation of showing how the Carnot cycle is realizing that maximum efficiency. But you can see pretty easily that if you're not creating any entropy in any of the steps, that you're going to be at the equality for the second law. So the second law says that the total entropy has to either increase or stay the same. But if we're explicitly constructing all of these steps such that it doesn't add any extra entropy, then it has to stay the same the whole time. So this actually does end up being the most efficient an engine could be. So why don't we actually make these? Like, these are so efficient, why not? Anybody have any thoughts about that? It's said explicitly in the book. Yes, they're extremely slow. So you can imagine if you've got a gas that is roughly at the same temperature of your hot reservoir, then heat is going to flow very, very slowly between them, right? Because the temperature differential isn't that great. So heat will flow, but it'll flow very, very, very slowly. So this process right here is going to take forever. And in real life, we don't typically like it when our energy comes at like a very slow rate. We're constantly sucking it up as fast as we possibly can. So if you tried to plug in your laptop or something to an engine like this, it would quickly just overrun its power capacities. So things like this are idealizations of how engines can work, but they're not actually useful. Not useful because slow. All right, so that's that. That's the Carnot cycle. Yeah. Mm-hmm. Mm-hmm. Okay, well, yeah, that's a good question. Let's go back here. So if we look at the efficiency for a heat engine, right? Theoretically, it's constrained by the difference between the cold reservoir and the hot reservoir. So if TC is roughly TH, then the efficiency is just 0, approximately, right? So you definitely want the hot reservoir and the cold reservoir to be at very different temperatures if you want to get any kind of appreciable efficiency. Does that make sense? Because like otherwise we'd just be describing a completely inefficient process. Yeah. Yeah, exactly. Like on this graph. So the gas starts here. It's at the same temperature all the way along this line, which is roughly T gas or T the hot, right? And then it undergoes an adiabatic compression or expansion, sorry, and the temperature decreases down to wherever T cold is. So it's these adiabats that are sending you in between the two different reservoir temperatures. And the farther apart you can get those, the better off you are, right? So I mean, it would be even better if you could have if this graph went on and on and on. If one of the isotherms was up there and the other one was way down here. Does that make sense? Yeah, yeah. The further apart you can make these two, the higher your maximum efficiency will be. Um, but the Carnot cycle, I guess in general, it's just telling you how you can construct something such that this is an equality. So I mean, you could just bring TC and T hot together, but then it's just you're getting nothing. Nothing's happening. Nothing's flowing. It just sits there. Yeah. All right. So that's that. Now let's wrap it up with refrigerators. We all love these. Okay, so what is a refrigerator? Well, it is basically just a heat engine, but in reverse. So now instead of getting out work, we put in work. So we can draw it like this. This is the hot res at T hot. Here is your refrigerator, which is again just some black box. I'll just call it fridge. And this is your cold reservoir at T cold. And so what you do is you plug in your refrigerator into your electrical outlet. Electricity provides some work, which sucks heat out of a cold reservoir and dumps it into a hot reservoir, right? That's what your refrigerator does. So the cold reservoir is like the inside of your fridge, And the hot reservoir is just your kitchen, effectively. So electricity's coming in through here. All right, so basically, yeah, all the same kind of ideas. It also, refrigerators and air conditioners are basically the exact same thing. It just depends on what you're calling your cold reservoir and your hot reservoir. I don't know if you've ever thought about that. You probably have. But like basically this functions as an air conditioner if you just turn it around. If now, yeah, the hot reservoir is like the outside and the inside of your room is the cold reservoir. So it's sucking heat out and dumping it outside. So how do we write the efficiency? Well, in this case, the benefit that we get is what? This heat right here, right? It's the amount of heat that we can suck out of our cold reservoir. And the payment is the electricity. So we define, rather than calling this the same thing, I guess, we're going to call this the coefficient of performance, just to delineate it from the other term. So we'll call it COP, coefficient of performance. And so this is just defined to be QC, what you get, over what you pay, work. So you can do the same thing again. We can use the first and the second law to get constraints. Well, what does the first law say? First law says that Q hot is going to be equal to Q cold plus the work, so just the total energy is conserved because it's a closed system. So we can rewrite the coefficient of performance using this, just rewriting this in terms of QC and then plugging it back in there. So that would give us, or sorry, yeah, I guess we'll rewrite work instead of QC. So we'll rewrite this as QC all over, what would that be? It'd be QH minus QC. And so now we'll do the thing that I've said many times before, and we'll do a magical thing known as multiplying by 1. So you can just rewrite this as Q hot over QC minus 1. All right, so now you just need to apply the second law in order to get the actual limit on what this is. This is going to be the best you could possibly do. So what does the second law tell us? Well, the second law tells us the following. It says that the total entropy has to either increase or stay the same, which just translates into the same statement that we had written before for the heat engine. So this is just the same statement. And if we rearrange this again, it's just the same thing, QC greater than T hot over T cold. So now we can put in the second law constraints on our coefficient of performance. And we would get that the coefficient of performance is now less than or equal to 1 over T hot over T cold minus 1. And then we can multiply by 1 to get this into a little bit of a nicer form. TC, T hot minus T cold. Okay, so let's just rewrite that. So coefficient of performance is less than or equal to TC all over TH minus TC. So we see now that a refrigerator is most performant, it's at its best, when the hot and the cold reservoirs are roughly the same, in which case this denominator right here blows up. So I guess now I would ask, does that align with your experience of real life? So let's take maybe your experience with living in the Midwest for a period of time. We all know that the summers can be pretty brutal, as can the winters be brutal. But in the summer, you have what? You have that the hot reservoir, the outside, is maybe not much greater than, but it really feels that way. It's greater than the temperature that you would like inside, right? So it's really hot outside and you want it to be like a cool 68 degrees in your apartment or something. Um, well, if this is much, much greater than this, then this denominator right here is big compared to TC on top, and so the coefficient of performance is really low. So during the summer, when you're trying to cool your apartment with your air conditioner, it's trying its best, but I mean, it just can't do that well because of the thermodynamic limits. So it sucks, but you got to pay more for electricity when it's hot out to cool your room. Does that make sense to everybody? Okay. I also wanted to just ask another conceptual question, which is why would you not want to put an air conditioner in the center of your room? Why do we put it in our window rather than just have an air conditioner that like sits in your floor or something? It should be pretty obvious. Yeah, exactly. Exactly. So yeah, I mean it would cool your room, but it would also just dump heat out the back. And so overall you would heat up the room. Yeah, it would function as the world's least efficient heater. So if you're ever in a bind and you don't have a heater, you can just take your AC out of the wall, put it on your floor and run it, but it's like a worst case scenario. Um yeah, I think that's about all I wanted to discuss. We're not going to talk about sections 4.3 and 4.4, obviously. Those are on real heat engines and refrigerators. If you want to learn about that and all the various different cycles that you can construct, you can read about that. But we're just focusing on the real theoretical underpinnings and the maximum efficiencies that you can possibly get right now. What sections of chapter 5? Yeah, that's a good question. So let me pull up the book real quick. I think that it's only going to go up through section 5.3. So for section 5, yeah, which we'll be starting next week, we're going to go from so we're going to go from the section 5.1, which is free energy is available work, up through phase transformations of pure substances, and then we won't talk about mixtures at all. We'll just talk about pure substances. So we won't talk about 5.4, 5.5, or 5.6. So yeah, chapter 5, if we were going to cover all the sections, it would be a crazy long chapter. Actually, all the chapters get a little bit longer as you get further into the book, so we'll leave off little bits here and there. Yeah, so make sure to read 5.1, 5.2, and 5.3 for next week. And then you get a new homework set on Monday, and then we'll start the fun all over again. Do keep in mind that we will have an exam coming up, not this coming week, but the week after. I think it's scheduled for Tuesday, which should be March 9th. So I'll probably make up another practice exam again because you guys like that, and post that. And I should also post the solutions like I said I was going to for the previous exam. I'll have those up soon enough, hopefully over the weekend. And yeah, the grader I think still has your homework too. I'm trying to get that back, but no guarantees at the moment. So are there any questions about anything in particular before we break? All right. Well, I will leave you to the rest of your day. I hope you have a good Friday and enjoy the rest of your weekend. And yeah, thanks for coming. See ya.